This video segment concludes our examination of biofuels in specific and transportation in general. Its major points are: number 1, procedures for direct burning of biomass, fermentation of sugars to ethanol, and cellulose purification are straightforward. Number 2, conversion of cellulose into ethanol is still inefficient. Number 3, the goal to replace 30% of oil use in the United States with alternative fuels by 2030 seems overly optimistic. Plant biomass has a low energy density in comparison to fossil fuels. In specific, maize kernels for starch, sugarcane shoots for sucrose, and switchgrass shoots for cellulose contain less than 1/3 of the energy in the equivalent weight of gasoline. It is not viable economically to transport such materials over long distances. Consequently, biofuel processing facilities are located near the sites of biomass production. For example, bioethanol processing facilities in the United States are concentrated in the Midwest Corn Belt. Transport for biomass to the processing facility, even over such short distances, contributes between 2 and 4% to total greenhouse gas emissions during bioethanol production. Some procedures for converting biomass to biofuels are as old as human civilization, where others still await technological breakthroughs. Well established are the procedures for direct burning of biomass, fermentation of sugars to ethanol, and cellulose purification. Still under development are efficient procedures to convert cellulose into ethanol. Anyone who spends time outdoors soon learns that starting a fire using wet wood is very difficult. This is because vaporizing any water in the biomass dissipates 2.27 megajoules per kilogram of water of the energy released during combustion. For this reason, drying biomass before combustion enhances its energy density as well as diminishes its transport weight. Drying biomass, however, proceeds too slowly in many regions of the world without ovens or kilns that themselves consume energy. Wood pellets, typically cylinders 6 mm in diameter and 10 mm in length, are a form of biofuels that travels well. They require only simple processing, have moderate energy densities, easily conform to packaging, and are safe to store. Processing entails harvesting the above-ground portion of trees, stripping off leaves and twigs, drying the raw wood from about 55% water to less than 10%, and forming the pellets in a die and roller press.
There's 3 rollers, and the tolerance is very tight to the die, and as there's the spinning process is actually pushing the sawdust through the die, and a friction is being created at that point and creates heat. And the process coming out the other end, the pellets they'll come out at a long length, but there's a knife that'll break them off. We're trying to aim for a 3/4 inch pellet.
So, you know, in the die process, I've picked up the pellets, and you can break them apart, but they are quite rigid. What is holding them together?
Just the lignin and the wood fiber.
Just the wood fiber. Yes. So it is just a really highly compressed, dried piece of wood.
That's correct.
These processes on average consume about 30% of the energy in the final product. Burning leaves, twigs, underbrush, and other so-called waste biomass can offset some of the energy requirements of pellet processing. Nonetheless, removal of such materials for energy purposes does not compensate for the loss of nutrients and carbon from the soils from which the biomass sprung. Long-term sustainability of biomass plantations is doubtful without periodic restoration of the soils.